Assalamualaikum class. I hope you're all fine. So here is the course content again. So far in our online classes, we have covered protein tertiary structure, which are the globular and fibrous proteins and enzymes as well. And now we will look at metabolism, and today we will start our series of lecture on bioenergetics and oxidative phosphorylation. Bioenergetics. Well, bioenergetics describes the transfer and utilization of energy in biological systems, while oxidative phosphorylation is the process in which the proton gradient runs downhill to drive the synthesis of ATP from a ADP molecule. It all happens or in the inner mitochondrial membrane. Now, bioenergetics makes us use of some basic ideas from the field of thermodynamics, particularly the concept of free energy. Changes in the free energy tell us whether a chemical reaction is energetically possible or not. Therefore, it can predict the feasibility of a chemical reaction. Now, bioenergetics concerns only with the initial and final energy states of a reaction components, not with the mechanism or how much time is required for a chemical reaction to take place. In short, we can say that bioenergetics predicts if a process is possible, whether kinetics measures how fast a reaction can occur. So let's get started. So first of all, let me tell you what Gibbs free energy is. For a simple definition, Gibbs free energy can be described as a measure of the amount of energy available to do work. The Gibbs free energy is simply a method of telling whether a chemical process will take place spontaneously or non-spontaneously. The Gibbs free energy calculates the amount of energy available in a system to do work, like carrying out a chemical reaction. Gibbs free energy is used in chemistry to help determine and predict ahead of time whether a chemical process is spontaneous or non spontaneous. You might be wondering what's the advantage of that? There are many applications in life that we need advanced knowledge. What to expect, for example, in the manufacturing of a product, if you have no clue what direction our process is going, then you might produce something totally unexpected and waste a lot of resources. The direction and extent to which a chemical reaction proceeds is determined by the degree to which two factors change during the reaction. These two factors are enthalpy, which is in this equation is represented by delta H, and entropy, which is represented by delta S. Now, enthalpy is the measure of change in heat content of a reactant and product, while entropy is the measure of change in the randomness or disorder of a reaction and products. Neither of these thermodynamic quantities by itself is sufficient to determine whether a chemical reaction will proceed spontaneously in the direction it is written. However, when combined mathematically, enthalpy and entropy can be used to define the third quantity, free energy or G, which predicts the direction in which a reaction will proceed spontaneously. Let's just briefly see what spontaneous and non spontaneous reactions are. A spontaneous process happens automatically. You might have to start off the process with a little activation energy and the rest will take care of itself. A good example of a spontaneous process is combustion, the burning of a substance to produce heat energy. While in a non-spontaneous process, a continuous energy input is necessary for the reaction to take place in a certain direction. A good example is photosynthesis, a process in which the plants make glucose. Now, photosynthesis requires energy in the form of sunlight to make the chemical reaction possible. Therefore, at night when it's dark and the sun is not there, photosynthesis does not work. So, a spontaneous process is the one in which no continuous energy input from the external source is necessary to run the process. while a non-spontaneous process requires a continuous energy input to run the process, like forcing you guys constantly to do your home assignments. Remember, only those events that lead to net increase in disorder occur spontaneously. So, keeping these things in mind, we can say that the Gibbs free energy is simply a method of telling whether a chemical process will take place spontaneously or non spontaneously. Another point to remember is that the Gibbs free energy is only applicable for systems under constant temperature and pressure. Now, what is free energy change or delta G? The change in the free energy is represented in two ways, either delta G or delta G naught, as you can see in this formula. The first G, delta G, which is without the naught, represents the change in free energy and thus the direction of a reaction at any specified concentration of products and reactants. Change in free energy, or delta G, then is variable. This contrasts with the standard free energy change, or delta G naught, which is the energy change when reactions and products are at a concentration of 1 mole per liter. Although delta G naught represents energy changes at the non-physiological concentrations of reactants and products, it is nonetheless useful in comparing the energy changes of different reactions. In this equation, delta G is the change in the free energy, while delta G naught is the standard free energy change, R is the gas constant, T is the absolute temperature. Molar concentration of A and B are the actual concentration of reactants and products, while Ln represents the natural log. The change in free energy, or delta G, can be positive or negative, and it can be used to predict the direction of reaction at a constant temperature and pressure, as I told you earlier. Now consider the reaction in this figure in which there are reactant A, which is changing into the product B. Look at figure A. Now, if there is a net loss of energy and the reaction goes spontaneously, which means A is converted into B spontaneously, the reaction is said to be exergonic, and delta G, or change in free energy, will be a negative number. But if there is a net gain of energy and the reaction does not go spontaneously from B to A, energy must be added to the system to make the reaction go from B to A. And the reaction is said to be androgonic, and delta G will be positive, as you can see in figure B. Delta G can also have a zero value, and it is the point when the reactants are in equilibrium. Now for reversible reactions such as the conversion of glucose 6-phosphate into fructose 6-phosphate. The free energy of the forward reaction is equal in magnitude but opposite in sign to that of the back reaction. For example, if the change in the free energy, or delta G, of the forward reaction is minus 5 kilocals per mole, then the backward reaction, its value is going to be plus 5 kilocals per mole. The change in the free energy of a reaction depends on the concentration of the reactants and products, and at constant temperature and pressure. And it can be calculated with this formula, which is written at the base of this slide. A reaction with a positive standard free energy can proceed in the forward direction, and it will have a negative overall delta G, or change in free energy, provided the ratio of product to reactant is sufficiently small, or we can say the ratio of the reactants to products is large. Now, looking at the reversible reaction of conversion of glucose into fructose, the one that I have described previously, the reaction conditions in which the concentration of the reactants, which is glucose 6-phosphate, is high compared as the concentration of the product, which is fructose 6-phosphate, delta G, or change in free energy, will be a negative value, despite the standard free energy G naught being positive. Thus, the reaction will proceed in the forward direction. Now let's look at the standard free energy change, or delta G naught. It is called the standard free energy change because it is equal to the free energy change delta G under standard conditions, that is when reactants and products are at a concentration of 1 mole per liter, like I told you previously. Now, under these conditions, the natural log of the ratio of the product to reactant is equal to 0. And therefore, when we put this value of 0 in this equation, the equation becomes this: delta G is equal to delta G naught plus 0. So we can say that the standard free energy or delta G naught is predictive only under standard conditions, as only then change in the free energy is equal to the change in standard free energy. However, change in standard free energy cannot predict the direction of a reaction under physiological conditions because it is composed solely of constants like gas or temperature constant, and therefore doesn't alter by any changes in product or substrate concentrations.